we've been talking about first-order linear systems that are homogeneous. So they fit this form x prime equals ax. Now, these systems can be solved directly. So it's an eigenvalue problem. A solution of this form ends up leading you to an eigenvalue problem. Now, we're going to focus on the 2x2 case. So that means our solution vector has two entries that are both functions. Through the eigenvalue problem and the eigenvalue approach, you can come up with formulas for x of t and y of t, and you can graph them if you'd like, and that is the most information you could possibly get. So that's very informative. Now, as an alternate way to interpret these results, we're going to talk about something called the phase plane analysis for this problem. Why would we do this if we have the formulas? Well, looking ahead, we are going to be dealing eventually with nonlinear systems that are much more difficult to solve, and that won't allow us to come up with formulas for the x of t and y of t. So that means we need to have another way to extract information from them. And it turns out that this phase plane analysis approach we take will work beautifully in those cases. Now, what is the phase plane? So the phase plane essentially says in a 2x2 system, don't look at x of t and y of t separately, but instead look at them together in the same plane and see what the relationship is. We are going to take both x of t and y of t as components or points in a plane. And they will end up being the parametric equations for point in this plane. So these are going to be parametric equations. And the curve that they trace out in time is going to be called a trajectory. And what we are after are the trajectories for our particular system. And so we would really love to know, how can we find trajectories? And by finding trajectories, there are lots of different ways. Now, one we could find directly, we could find them directly from the x of t and y of t formulas. And we can do what's called eliminating the parameter, where we try to get rid of the t, and we try to come up with some equation y equals f of x. And this is going to give us a curve or equation for the trajectories. Now, if this works, it won't work for every single case, and sometimes we might run into trouble, but it's a very convenient way of doing things. There's another option. We can try to find things directly from the slopes. Remember, in a linear system, we are given x of t and x prime of t and y prime of t. So that means by the chain rule, we can determine the relationship for the slope of the parametric equation. So that means we can solve this first order dE to get y of x. Now we're going to do this later in the course. We won't take this approach now. The reason it's difficult is because those equations are typically nonlinear, and it becomes more involved to solve them. Now, another way to deal with phase plane trajectories is to talk about them qualitatively. Qualitatively means no formulas. We won't be able to come up with any formulas of any kind, but what we will do is use the eigenvalues and the eigenvectors to sketch out the trajectories. And while we won't have any formula to compute numbers with, we will be able to understand how the solution behaves. And that's what's really important. We are interested in what the solutions to these problems will do. We don't necessarily care about whether we can get formulas for them. Formulas are wonderful, so when we can do option 1, we'll take it. But sometimes we have no choice but to resort to 3. Regardless, having all of these tools in our toolbox is really important. For the 2x2 case, we're going to have different situations for our lambdas. the lambda cases are just like we expect. We should have real and distinct eigenvalues. We could have real and repeated eigenvalues, or we can have complex. And remember that when an eigenvalue is complex, it comes in a conjugate pair like this. So we'll start with lambda being complex because it's a nice way to show you how to eliminate the parameter and get some useful information. So if we start with lambda as complex, there are really two cases here. The pure imaginary case, where lambda is plus or minus I beta, versus the full complex, where alpha plus I beta exists. Now this alpha is the real part of the eigenvalue, and that's important. Now, as an illustration of this purely imaginary case, here's an example that's been considered. We have a 2x2 system. It has eigenvalues of plus or minus 2i, so they're pure imaginary. You can take those eigenvalues, figure out the eigenvectors, and form the solution in terms of real functions, sines, and cosines. So you can pause the video if you'd like. You can take a look at previous notes, but the two individual component solutions look like this, y of t and x of t. Now, to get an equation for the trajectories, I'm going to start by looking at this y of t equation. Now, the y of t equation is a sum of sines and cosines. Trig identities exist that allow us to take multiple sines and cosines and add them together into a single cos. So, for example, if I wanted cos of 3t minus beta, it can be written in this way. Of course, I can also scale it by multiplying everything here through by some constant r. And if I do this and I want to equate y of t to this, that means I need the following to be true. I need r cos beta to be C1. I need r sine beta to be C2. This will allow me to determine r and beta. Now remember, C1 and C2 come from specified initial conditions. If I give this system initial conditions, I'll be able to find C1 and C2, and there'll be specific numbers. This will allow me to compute a specific r and a specific beta. So given that I can find C1 and C2, if I square both of these equations, I'll end up getting r squared is C1 squared plus C2 squared. So this will tell me that r should be the square root of this expression. And tangent is sine over cos, so I can find here that the tangent of that phase angle is simply going to be C2 over C1. So if I needed a specific number, I could always compute this. So what this is going to tell me is that y of t could be written as some r cosine of 3t minus beta. Now, up here for x, there's a similar equation. The difference here is that there's a negative sign and the order of the terms is a little bit different. Now, similarly, I'm going to take this approach. I could write r sine of 3t minus beta as r sine 3t cos beta subtract r cos 3t sine beta. Now, this particular form is chosen for a couple of reasons. Number one, it mirrors what's given there in the x equation. And number two, we're going to need it to eliminate the parameter. Now, just to be a little bit more general, rather than calling it r, I'm going to say it's some k. And what I'll find is that if I want the x equation to match this, what I will need is that k cosine beta is going to have to be 3c1. And in the second case, k sine beta is going to have to be 3c2. So again, you can pause and take a look and see what needs to happen in order to make this match. But what we'll find here is that k is going to end up being 3 times c1 squared plus c2 squared, which means that it's 3 times the r value I got for the other term. As before, tangent of beta is still going to be c2 over c1, so it's the same beta. Now, the point of all of this is that we can take the two solutions and write them in a more compact, more straightforward way. We'll have 3r sine of 3t minus beta, r times the cosine of 3t minus beta. This allows us to eliminate the parameter. The equation of an ellipse is the way for us to eliminate this parameter. And in particular, if I were to take x squared and divide it by 9r squared and y squared over r squared, this would end up giving me a 1. Again, this is the equation of an ellipse. And depending on the value of r, so depending on c1 and c2, I'll get a differently sized ellipse. And in this particular case, the x-axis is going to be longer, 3 times longer than the y-axis. So regardless of what that value of r is, they'll always have this sort of relationship. Now remember, x equals 0 is always a solution to every homogeneous problem. It is, in this case, it's called a center because you've got these closed trajectories going around them. And the trajectories, the x equals 0 is at the center of all these trajectories. Now, if you wanted to find the direction of the motion along these trajectories, you can pick different values of t and then determine what x and y are and see how it evolves in time. Now, in this particular case, it would sort of rotate around in this way here, but it's not so important. That can be done. So that's a specific example of what can happen generally in the case of complex, purely imaginary lambdas. So generally, when lambda is this plus or minus I beta, you're going to get some sort of circles. Circles will happen when you have exactly the same amplitude for each of those terms. You could get the ellipses like we talked about. Now, they don't have to be on the x-axis, longer on the x-axis. They could be longer on the y-axis. But more generally, you could expect to get some sort of rotated ellipses. And this is the most general version of all of these things, where you're going to have some sort of ellipse that's stretched along a given direction. All of these situations will arise from the purely imaginary eigenvalue case. They're all considered to be centers. And the centers are important. They're going to give you this impression that the behavior repeats itself. So this is indicative of repeated or periodic solutions. You can see that in the phase plane, the x and y values will always return to a given point. They'll travel along a trajectory and they'll always return to a given point. So this, in terms of the mass spring manner of thinking, this has something to do with no damping, no friction. There's no loss here where everything is beautiful and periodic. The other case is when you have when you have fully complex. In the case of fully complex, the sign of this alpha is going to be very important. As a specific example of this, here's a system that has complex eigenvalues, -1 plus or minus I. And if you go through the mechanics of plugging it in, solving for the eigenvector, you'll find that this ends up being your solution. Again, if you want to pause the video, you can go ahead and do that and determine the eigenvalues and eigenvectors. individually, the solution components look like this. And if we go ahead and repeat the analysis we just did, so if we do the same thing we did above, you'll be able to rewrite this as e to the minus t sine of t minus beta, and y of t will be e to the minus t cos of t minus beta. So you'll be able to compactly put this thing together, and there'll be an r here. E to the minus t r sine beta, e to the minus t r cos beta. In this particular case, they'll have the same r, but that doesn't have to be the case generally. We're going to eliminate the parameter. And when we eliminate the parameter, what we'll find is x squared over r squared, y squared over r squared will end up being e to the minus t squared. X squared plus y squared will then be r e to the minus t all squared. So this is a circle where the radius will end up going to 0 as time goes to infinity. So at each moment in time, the location of the trajectory is found by the equation of a circle, but at every moment in time, that circle shrinks. So this is what's going to happen. This point x equals 0 will end up being what's called a stable spiral node, meaning all the solution trajectories, depending on where you start, it's actually irrelevant. At all points, everything will eventually make its way to the origin in a circular decaying fashion. So it's a stable spiral. And it's stable because the real part of the eigenvalue is negative. That negative real part leads to a decaying exponential and a decaying radius. Now, in general, when we have this lambda as alpha plus or minus I beta, two options are possible. If, as we just discovered, if the real part of the eigenvalue alpha is less than 0, you'll have what's called a stable spiral node. Now, these nodes could be circular, they could be elliptic, they could be a rotated ellipse. It doesn't matter, but what will be important is that they will all spiral in to the origin. And if the real part of this lambda, which we're calling alpha, is greater than 0, we'll have what's called an unstable spiral node, because all the trajectories will leave x equals 0 as time goes to infinity. So you'll get a reverse picture. Everything will spiral out from the origin. So the totality of everything that can happen here is related completely to the fact that the imaginary part leads us to this circular repetitive motion, but the real part of the lambda is what determines whether it grows in time or decays in time.